electron concentration in intrinsic semiconductor. In a given intrinsic semiconductor, what is electron concentration? What is electron concentration definition we are discussing now? Intrinsic means pure semiconductor. Pure means already we said germanium or silicon. The semiconductor which is prepared by germanium, the semiconductor which is prepared by only silicon is called a pure semiconductor. In this pure semiconductor germanium or silicon, electron concentration we have to find, we have to calculate. So what is electron concentration? The number of electrons per unit volume. In this conduction band we have taken a conduction band of given material. In this conduction band it is a unit volume. In this volume how many number of electrons are there? That is called what? Electron concentration. Now I am explaining once again the electron concentration in a given semiconductor. Given semiconductor means germanium, or if it is given silicon. In this germanium or silicon, whatever it may be, which is given in that semiconductor, we are going to have valency band and conduction band. Conduction band I am saying as a CP band, conduction band. Valency band I am representing here VB band, VB, valency band. So in the conduction band I am taking a unit volume. This is a unit volume. In this unit volume, how many number of electrons are present? That is called what? Electron concentration. That is written in the form of definition. The number of electrons per unit volume of conduction band of given intrinsic semiconductor is called electron concentration. It is represented by small l. Now we are taking a conduction band. In this conduction band we are taking a part of conduction band. The conduction band part we are taking E2 E plus DE energy levels we are taking. Means whatever the electrons are present in this E2 E plus DE energy levels, those are having energies of E2 E plus DE. So in this case, carefully if you observe, I am taking a unit value. In this unit value, how many number of electrons are present? That is called, already I said, carrier concentration. That is represented by N of E D. Once again I am saying, I am taking a conduction band. In the conduction band I am taking a part. The part of energy level energy is E2 E plus DE. In this E2 E plus DE energy levels, most of the electrons are having E2 DE E plus DE energies. So in this E2 E plus DE energy levels, I am taking a unit value. In this unit value, how many number of electrons are present? That is called carrier concentration N of E DE. I am writing here. Means the number of electrons present in this unit value I am writing N of E DE. Put the energy levels E2 E plus DE. Now the same thing we said here. Let number of free electrons per unit volume of conduction band having energies E and E plus DE represented by N of E DE. Once again I am repeating. Let number of free electrons per unit volume of conduction band having energies E and E plus DE is represented by N of E DE, E2 E plus DE. Between these two, how many number of electrons are there in this unit value? That is represented by N of E DE. This N of E DE we can obtain. How we can calculate N of DE means we have to multiply Z of E DE with F of E. See, N of E DE is equal to ZC of E DE into FC of E. So ZC of E DE is a what? Density of energy states. nothing but number of energy states per unit volume. Here you can see in this unit volume the number of energy states. In this unit volume the number of energy state is Z of E dE. Number of energy levels per unit volume is Z of E dE. Number of electrons per unit volume is this one. So if you want to get this one, number of electrons per unit volume, if you want to get it, this value you have to multiply with Fermi Dirac distribution function f of E. With this function you have to multiply. That is in this sentence. So NEDE is obtained by multiplying the density of energy states Z of EDE. Density of energy states means number of energy states per unit volume. Already I shown here. Number of energy states per unit volume is this one. Then and which you have to multiply the Fermi Dirac distribution function f of E. This one and this one if you multiply you will get this one. That is written here. This is equation number 1. Now the total number of electrons in conduction band. Now the total number of electrons in the conduction band per unit volume between energies EC to E are calculated by integrating above equation. Means here you have to understand one thing. Now we have to calculate in this total conduction band how many number of electrons are present. In this total conduction band we have to calculate total number of electrons. To calculate this one, what you have to do is first the conduction band is expanded from EC to ECT. Conduction band lower energy level to conduction band highest energy level, that is called ECT, top of the conduction band energy level. This is now total number of electrons we have to calculate n value. That is why to calculate this one already we know one equation. That is N of E dE is equals to ZC of E dE F of E. This is only the number of electrons per unit value. Only this is what, sir? Number of electrons per unit value. But now we want to in this unit volume the number of electrons per unit volume is N of E dE is equal to ZC of E dE F of E. This is called number of electrons per unit volume between the energy level EC2 E2 between the energy levels E2 E plus dE. That is E2 E plus dE, the energy level number of electrons per unit volume is this one. That we are getting by multiplication of between energy density to Fermi Dirac distribution function. Already we know it. So N of E dE is obtained. What number of electrons in this unit volume is obtained by multiplying Z of E dE energy density states, energy state density Z of E dE and multiplied with the Fermi Dirac function, then we are going to get a N of E dE, means number of electrons in this unit volume we are going to get it. So here, but only we know N of E dE means what? In this unit volume how many electrons are there, that only we know. But we have to calculate from the bottom of conduction band to top of the conduction band how many number of electrons are there. To do that one, what you have to do is, this equation is there, no? This equation we have to integrate both sides. This equation we have to integrate both sides. So when you integrate this equation, this I can say simply For understanding, I can say integration of only dn. I can say dn. I can say dn. dn. I can say. So if you integrate dn, what happens? n you will get it in this place. If you integrate dn, in this place you are going to get n. And integration, we have to do it right side. N of e dE for this integration, you have to take from the conduction band bottom to top of the conduction band, you have to integrate in this equation. So EC to ECT N of e dE you are taking, that's why. Means in this side, left, in the right side, you are getting integration value from EC to ECT. Why? Because here, from here to here we have to calculate total number of electrons. So integration, you have to do it both sides. So then we are getting like this. This is equation number 2, say. But now what we are doing, this value we are splitting into two terms. EC2 to ECT, we are splitting into two terms like this. The conduction band bottom energy level is EC, top energy level is EC2. But between EC to ECT, infinitive energy levels are there. That is why I can write EC to infinitive and infinitive to EC. Like this, total integrations I can split into two terms. Like this, you can see here. The above equation from the diagram I can writing n is equal to, as it is, you can see that n as it is, but what we are doing here, integration of EC to ECT, that we are splitting into two terms, EC to infinitive, means EC to infinitive and infinitive to ECT. See, infinitive to ECT n of dE. Like this one term is split into two terms by using this diagram. Now, from above equation, from this equation, I can say n is equals to what? EC to infinitive n of dE, the same term as it is written, but one change we have done. This integration lower limit made as a upper limit made as a lower limit. That exchange is done according to mathematics. When you exchange the lower limits and upper limits, then automatically this value plus is going to become as a minus. So this equation is a fourth equation. Now we are taking another equation. So just we have discussed here, n is equal to EC to infinitive n of dE minus EC to infinitive n of e dE is equal to fourth equation. This fourth equation is saying in the above equation the second term vanishes, means this term becomes 0. The second term becomes 0, equal to 0, because what he is saying is in the above of ECT, in the above of ECT, 0 electrons present. In the above ECT, we are having how many electrons? 0 electrons. That is why this gives you, this value gives you is equal to 0. Same explanation we can see here. EC to ECT, ECT above energy level, no electrons are present. That is why this term represents what? Above ECT, this term represents, this term n is ECT to infinitive n of e dE represents what? Above ECT energy levels. In these energy levels, electrons, number of electrons are 0. That's why I am writing here 0. So in the fourth equation this will be removed. Finally in EC2 integration n of e dE will get it. See, n is equal to EC2 infinitive n of dE we are getting. But now already we know n of e dE is equal to ZC of e dE f of e. Already in the starting equation we have taken. You can see that equation also here. From equation 1, N of E dE is equals to ZC of E dE FC of E. Means in this equation, the first equation, this is the first equation or this is first equation. This first equation already we calculated, that equation we are substituting here. Then this is going to become as like this. Means fourth N is equal to EC2 infinity to N of E dE value. We are right in this one, N of E dE value from the equation 1 it is there. This value we are substituting here. Then what happens? N is equal to EC2 infinity to ZC of E dE F of E, as it is we are substituted in the equation number 5. But Fermi energy level Fe FC of E means Fermi Dirac distribution of electrons. So electron distribution is done by Fermi Dirac statistics. So from the Fermi Dirac statistics, F of E value is 1 by 1 plus e power of E minus EF by kT. But if you see here, if you assume the value of E is greater than EF, means this value is more than this value, it is greater value, it is less value, then we can get total entire this value is going to become more and more, and then we can neglect 1. That is why we are writing 1 plus e power of exponential E minus EF by kT. E power of E minus EF by kT. In this one, the entire time is more value than 1 value. That is why we are neglecting what? 1. Finally, with this total, this entire term, in the entire term, this is only remains, it is neglected. Why? Because E is greater than EF. In this equation, E is greater than EF. That is why total term value is going to increase. This is going to be neglected. So only one term is this term only remains. There this one value we are neglecting. So E is equal to E minus EF by kT. Finally we are getting. So final F of E is equal to 1 by 1 plus 1 is neglected now. So only remains E minus EF by kT. That is there. So if it is in denominator, now we have, if you bring it as a numerator, E minus EF minus E by kT we are getting. So finally we got distribution function of electrons is F of C of E is equal to E power of EF minus E by kBT. We got already, just we have got. This is equation number 7 say. But we think what Z of E, Z of E D is called density of energy states, density of electron energy states. So that is ZC of E dE. But ZC of E dE value according to statistical mechanics, pi by 2 8 me star by h square whole power 3 by 2 into e power 1 by 2 dE. This is equation we got from statistical mechanics for density of energy states. Now in this equation, here in this equation, in the place of E, we are taking, in the place of E, we are writing E minus EC. E minus EC. It is a bottom of conduction band energy level. E is a energy level between, in between EC to ECT. You can see here the picture. This is the bottom of energy level of conduction band. This is the energy level which is present in the conduction band at any place you can take. I am taking the middle. Same way, then this E value is going to become like this, E minus EC, because we are taking two energy levels, electrons are spreading, we are taking EC to E, I am taking, that is why in the place of E we are writing here, in the place of E we are writing E minus EC we are writing. So here also EC is more than EC, E is more than EC. In the figure, energy E value is greater than EC. That is why we are writing in this place E first, this E value first here, next bottom energy level conduction band, this one here. So in this place like this we are substituting. Whole power of 1 by 2 dE as it is. This equation I am taking it as a 9th equation. Z Fc of e power of e minus e by kBt function, distribution function of Fermi Dirac distribution function f of e value, and energy density that C of e dE value we are substituting in this equation. Sorry, in this equation. So this C of e dE, Fc of e, in the fifth equation we are substituting Fc of e value, Zc of e dE value. See here. So if Fc of e value already we got e power of ef minus Vc by kBt. This we are substituted here. Next, Zc of e dE that we got here. Zc of e dE pi by 2 8 pi square m e star by h square whole power 3 by 2 e minus ec whole power 3 by 2 e. This equation we are substituting here. And finally, if I substitute that, 7th, 9th equation in 5th equation, we are getting n is equal to ec minus ec to infinity to, limits are ec to infinity to pi by 2 8 me star h square whole power 3 by 2 e minus ec whole power 3 by 2 whole by 1 by 2 into dE. This total pi by 2 to here, this value is called, this is z of c of e, dE value is this one that we have substituted here up to here dE. This total value substituted here. Next, this value is from this one. This value here we have substituted. So finally n is equal to Zc of e dE into f of e values we have substituted here. Then we are getting C. Ec to infinity, here pi by 2 is constant, 8 me star h square, integration of ec to infinity 2. Okay, next, these are the constant values we are writing outside of integration. This is e minus ec as this we are writing here, whole power 1 by 2. It's a variable value is having here e, that's why we are writing inside only. Next, e power of ef minus e by kBt as it is I am writing. Kb means Boltzmann constant. Equation number 10. In this this integration we are doing by substitution method. Let e is equal to e minus ec. E minus ec taken as a small e. So if you integrate both sides, dE is equal to e minus and e d is equal to this only variable, that's why this differentiation is dE. This differentiation is dE, this differentiation is dE, this differentiation is 0. Why? Because ec is equal to constant. So if you write here limits, we have to write here. What you have to do? This value, limit value, you have to substitute here, lower limit value. Then ec if you substitute in the place of e, ec minus ec 0. So e is equal to 0 that we got here. Next, higher limit infinity. If I substitute infinity in the place of e, infinity minus ec, infinity only. So e is equal to how much? Infinity we are getting. That's why we are getting higher limit. These limits also we got. Now, so in the 10th equation, n is equal to 1 by pi by 2 as this 10th equation writing 8 me star by h square whole power 3 by 2 already we got in the previous equation. And see, as it is we are writing. Same equation we are writing here. But limits are the 0 to infinity. 0 to infinity means ec is, if substitute I got a 0 limit. If substitute infinity here, infinity. So that limits you are getting 0 to infinity. Next, e this value. You can see that e minus is equal to what we thought? E. That value we are substituting here. So here we have substituted. Next, but one thing cautiously remember that e power of ef as it is, but in the place of e we have to substitute this e value here only, this ec value being that side. Then it becomes like this. E is equal to this value that side if you send it, plus EC. Means here E is there. From this equation, E value we are getting like this. Means E you have to keep here only. This value you have to bring this side. Then small e. This bit goes outside, plus it becomes. So E value. This E value you have to substitute. So EF only. In the place of E, we are writing this value E plus EF. So E plus EF it by kBt exponential dE as it is, we got it. Now third step if you go pi by 2 at m star by square whole power 3 by 2 as it is. But here one term is there. EF is a constant, EC is a constant. So here if you open the bracket with minus EC will get it. So what you can write, e to the power of EF minus EC, e to the power of EF minus EC by kBt. I am writing outside. Why? Because this term is a constant. EF is constant, EC is constant, the constant terms I am writing outside. What remains here inside the integration 0 to infinity as it is, 0 to infinity is this, e power of 1 by 2 as it is. But here only one term, EF already has gone outside from integration, EC also has gone outside. So minus E by kBt dE. So this dE is equal to, already said, dE is equal to, capital D is equal to small d. Like this you got a substitute. So now if carefully observe, next step, the same terms are going to be repeated as it is, but here the same term is repeated again. The same term we are writing once again like this for clarity. But here what you have to do is this term integration only we have to do. Remaining are constant. From here to here total is constant is keeping outside, keep it aside. Now we are taking only integration term. This is only integration term. So integration of 0 to infinity to e power of 1 by 2, e power of minus e by kBt, this is here, into dE. Its value is, after integration we are getting directly, the value is root pi by 2 into kBt whole power 3 by 2, equation number 12. This you have to remember, that's all. You can, if you have the patience you can do it, but it takes much time. Why you are wasting your time? It's a physics, you have to do all the derivation also, which is important. What we have to take it, already derived it is. So this integration value means this part of integration value we got root of pi by 2 kBt whole power 3 by 2 its values. So directly you can substitute here. This value you can directly substitute here in this equation. So then if you substitute, so pi by 2 as it is, just we have seen 8 pi square 8 me star by h square whole power 3 by 2 e power of ef minus ec by kBt. But integration value how much? Pi root pi by 2 kBt whole power 3 by 2, we got it. So here what are the terms you have to remember is pi by 2, this pi by 2 and this root pi by 2, root pi by 2. So pi into root pi is written as a pi power 3 by 2. So I am writing inside it. So here 3 by 2 in the, so I can write it, I can give a small calculation for this. Pi by 2 into root pi is equal to pi power 3 by 2. So pi power 3 by 2 is this pi by, already it is 3 by 2 is 8 me star over 3 by 2 square is. So this pi by 2 also you can write inside. So that's why I am writing here. Of this and this multiplying, and then the value is pi of 3 by 2. Already 3 by 2 is there, so I am writing here. Next kBt already is having 3 by 2. So this also we are sending into this bracket. So this root pi into pi value is getting pi power 3 by 2. That also we have sent into the whole power 3 by 2 by 3 by 2 whole power bracket. And kBt is also having the 3 by 2 whole power. So the kBt is also bringing inside h square. So we are simplifying, synchronizing, simplifying we are doing. So here by 2 is there, by 2 is there. So 1 by 4 we are writing. Next what remains? E power of ef minus ec by kBt. Thus ef minus e power of ef minus ec by kBt as it is we are writing. So simplify it is fine. Now, so here we are writing this 8 is there. 8 I can write as a 2 cube 8 this 2 cube, you can write 2 cube I can write. So 2 cube means 4 2 I can write 2 square into, you can write here simply I can tell you some information about this. You can see carefully. I am writing here. For example, I am taking here simplification I am showing here. So what I am doing, okay, 8 is this value I can write 4 into 2 pi. This value I am writing, here pi me star kt kbt pi h square is equal for 3 by 2. So here what I am doing is, this I can write as like this. 4 means 2 square into 2 whole power 3 by 2 is there. See, 3 by 2 is there. 8 I have written as a 4 into 2. So 4 I can write as 2 square. So if I write 2 square whole power 3 by 2 into 2 power 3 by 2. So this square, so 8 remains 2 power 3 by 2. So this value we are getting 8 into 2 power 3 by 2. So this 8 I am writing outside powers, this 2 I am writing here, this 2 gets cancelled. So 2 power 3 by 2 power 3 by 2. So 8 into, so this 8 we are getting like this, 8 into 2 power 3 by 2. So 2 power 3 by 2 is that is writing I am inside only, which is 8 only, that I am writing outside. 8 by 4 we are getting. So only this term 8 I am writing like this, 2 square into 2, and open the open this 4, then we are getting 2 square a whole power 3 by 2 and 2 power 3 by 2 I am getting. 2 is 2 cancel, 2 cubic happens, so 8 we are getting. So here 2 power 3 by 2 as it is, so 8 can be written as a 2 inside. Why? Because it is having 3 by 2, so inside I am writing. It is not having 3 by 2, so writing I am outside, so 8 by 4 happening. So as this pi is pi and kb is kb, t is t whole power 3 by 2, h square is h square, as t whole power 3 by 2 writing. So as it is writing, no change at all. Now final equation is equal, n is equal to what? Here one term you have to remember, 4 2 8, so 2 me star pi kbt, 2 me star pi kbt as it is by h square whole power 3 by 2 whole by 3 by 2 e power of, but we are done here conduction band minus Fermi Lami's law, minus take common, the writing this is the 13th equation, which is going to represent carrier concentration of electrons in the conduction band for given semiconductor. Here we are simplifying this equation, this 2 into 2 pi m 2 me star pi kbt by h square, this whole power 3 by 2, this term I am taking it as a nc, I am assuming that nc, so here I can write nc, same as this I am writing. So this is a electron concentration in intrinsic semiconductor.